So this morning we're going to continue on to yesterday's lesson, which was solving problems using tables and diagrams. So just a quick review from yesterday. Odds in favor is the number of outcomes for event A to the number of outcomes against event A. Odds against A is the number of outcomes against A to the number of outcomes for A. Then we have mutually exclusive and non-mutually exclusive events. If two events are mutually exclusive, meaning their Venn diagrams don't overlap, it can either be a member of this group or that group, but not both, then the probability of A or B is the probability of A plus the probability of B. If they are not mutually exclusive, meaning they could be members of both sets, so a student could be blonde and walk to school, she doesn't have to be one or the other, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B, that overlap area. Then we have independent and dependent events. If the events are independent, meaning the outcome of the first event does not impact the second event, then the probability of A and B is the probability of A times the probability of B. If they are dependent, meaning the outcome of event A affects what the outcome of the second event is, then the probability is event A times the probability of event B occurring, given that A already happened. So yesterday we looked at the first example on the tables, and I gave you question number 1 for homework. So what we're going to look at today is we're going to look at using tree diagrams to help us calculate these probabilities. Students are given the following problem. The odds that Ava will pass math this semester are 4-1 in favor, and the odds that she will pass math this semester are 1-9 against. If these events are independent, meaning her ability to pass math does not depend on her ability to pass English, determine the probability that she will pass math and English, math and not English, or math or English. So question A says, express the odds in terms of probabilities. So the probability that she will pass math. Well, the odds in favor that she will pass math is 4-1. Probability is out of the total. So the total would be out of 5. The probability that she will pass math is 4 out of 5. So that's 0.8. That's the probability that she's going to pass math. The probability that she will pass English again, probability is out of the total. So when it's odds for or odds against, it's a part-to-part ratio. So if I add them together, I get the total. This ratio is 1-9 against, meaning that there's 1 chance against her passing math and 9 chances for her passing math. So English. So the probability that she will pass English would be 9 out of 10, or 0.9. So some of the students chose to use probability formulas to solve the problem. Show this method of the solution below. So the probability that she will pass math and English. So these are independent events. The probability that she will pass math does not depend on the probability she passes English. So that becomes the probability of math times the probability of English. So that's 0.8 times 0.9, which equals 0.72, or she has a 72% chance of passing math and English. The probability that she will pass math and not English, that becomes E prime for not English, not passing English. So probability of math times the probability of not English becomes 0.8 times 0.1, which gives me 0.08. So she has an 8% chance of passing math but not passing English. And finally, math or English. So the symbol for that should actually be the U. So there is some overlap here. She could pass math and she could pass English. So these are not mutually exclusive. So this becomes the probability of math plus the probability of English minus the probability of math and English. So this becomes 0.8 plus 0.9 minus the 0.72 that we got in the first one. And that will end up giving me 0.98. So she has a 98% chance that she's going to pass one of the two subjects, or both. Other students decided to use this in a tree diagram. So if I have a tree diagram, we look at the first outcome. The first outcome is passing math. The probability that she will pass math is 0.8. The probability that she would not pass math would be 0.2, because together it has to add up to 1. Either she passes math or she doesn't. The probability that she passes English is 0.9. The probability that she does not pass English becomes 0.1. So if I follow the tree diagram, the probability that she passes math and English becomes 0.9 times 0.8, which is 0.72. The probability that she passes math and not English becomes 0.1 times 0.8, or 0.08. Then down here we have the same outcomes that we had up here. The probability of passing English is 0.9. The probability of not passing English is 0.1. So the probability that she passes, that she does not pass math, but she passes English is 0.9 times 0.2. Which is 0.18 or 1800ths, or an 18% chance. The probability that she does not pass math and she does not pass English is 0.1 times 0.2, which is 0.02. So 2% chance that she would fail both subjects. So when I'm doing a tree diagram, the outcomes of math, the probability becomes here, and then the second probability for the outcomes is the same, 0.9 and 0.1, 0.9 and 0.1. And then to get the combined, I multiply. So let's go into the next one. In a game of field hockey, the probability that the Dinos score a goal from any short corner is 1/8. During the first half of the match, they are awarded 2 penalty corners. Use a probability tree diagram to determine the probability that from these 2 short corners, the Dinos will score 2 goals, 1 goal, at least 1 goal, so they can score 1 or 2, and no goals. So the probability of scoring a goal is 1/8. And we're going to leave it as a fraction because as a decimal, it's like a 3-digit decimal. So we'll just leave it as a fraction. So if the probability that they score a goal is 1/8, the probability that they don't score a goal is 7/8 because it has to add up to 1. So that's the first goal. Either they score a goal or they don't. Then we have the second outcome. They score a goal or they don't with the second shot. They score a goal or they don't with the second shot. The probability that they score is 1/8. The probability that they don't is 7/8. The probability that they score a goal is 1/8. The probability that they don't is 7/8. If at any time you think I'm going too fast, pause, or ask Mrs. Newlett to pause so that you can catch up. The arrows here point to my outcomes. So if I follow the tree diagram, I have a goal and a goal. So the probability of scoring one goal and another goal, so it's the probability of scoring my two goals, is 1/8 times 1/8, which is 1/64. So they have a 1 out of 64 chance of scoring two goals on these penalty shots. The probability that they score a goal and they don't score a goal, that's following this line in here. So that becomes 1/8 times 7/8, which becomes 7/64. Then we have the probability that they don't score on their first shot, but they score on their second. So no goal and a goal. So no goal is 7/8. Goal is 1/8. Which again gives me 7/64. And finally, the probability of no goal the first time and no goal the second time becomes 7/8 times 7/8, which is 49 out of 64. If I add these numbers together, 1 and 49 is 50, plus another 14 is 64. This will always add up to one whole, which it should, because my probability should add up to 1. So the probability that the Dinos score two goals is right here, 1/64. The probability that they score one goal is 7/64 here, and another 7/64 here. So that's 14/64, or 7 out of 32. For C, the probability that they score at least one goal, there's one goal, or they could score two. So I have 7 out of 64 plus 7 out of 64 plus 1 out of 64 for a total of 15 out of 64 chances that they could score at least one goal. And finally, the probability that they do not score a goal at all is 49 out of 64. So you can use a tree diagram to help set your questions up. If you find that you can organize your information better, use a tree diagram. If you find that you organize it better with a diagram, use a diagram or the table. Okay. What we're going to look at now is what happens if the events are dependent, if the outcome of one affects the outcome of the other. Cheryl is trying to show John how to solve problems based on the following information. Two machines, A1 and A2, produce all the glass bottles that are made in a factory. The percentage of broken bottles produced by these machines are 5% and 8% respectively, which means A1 breaks 5% of the bottles, A2 breaks 8% of the bottles. Machine A produces 60% of the output, meaning machine A2 would be the remaining 40%. Cheryl suggests the following strategy. Introduce symbols to represent the information, write the given probabilities in terms of the symbols, and set up a probability tree diagram. So complete John's work, which is started below. A1 is that the bottle is from machine A1. A2 is that the bottle is from machine 2. And the probability of B is that the bottle is broken. So the probability that the bottle comes from machine A is a 60% chance, which becomes 0.6. The probability that the bottle produced comes from machine A2 is the remaining 40%, or 0.4. So the probability it comes from A2 is 0.4. The 5% breakage is the probability that the bottle is broken given that it came from machine A1. And the 8% becomes the probability that the bottle is broken given that it came from machine A2. John now sets this up into a probability tree diagram. The first branches are leading to the machines, and the second set of branches leads to it being broken and not broken. So the probability of event A1 is 0.6, probability that the bottle comes from the first machine. The probability that the bottle is broken, given that it came from the first machine, is 0.05. Which means the probability that the bottle is not broken, given that it came from the first machine, would have to be 0.95. It has to be the leftover amount. These two together have to add up to 1. So the probability of it coming from the first machine and it being broken is the probability of A1 times the probability of event B given that it came from A1. The probability that is broken and it came from the first machine. So this becomes 0.6 times 0.05, which gives me 0.03. So there's a 3% chance that I'm going to have a broken bottle from machine A. Then this probability is the probability that it came from machine A and it's not broken. So that's the probability of machine A1 times the probability that it is not broken given that it came from A1, which becomes 0.6 times 0.95, which equals 0.57. And then I can follow the same outline for machine A2. So if there's a 60% chance or a 0.6 probability that it came from machine A1, the probability that it came from machine A2 would be 0.4. The probability that it is broken, given that it came from A2, is 0.08. And then the probability that it is not broken, given that it came from A2, is 0.92. And again, it's because these two probabilities had to add up to 100. And this is my not broken symbol. So now if I follow this through, this arrow would represent the probability of it coming from machine 2 and it being broken. So that's the probability that it came from A2 times the probability that it was broken given that it came from A2. This equals 0.4, the probability that it was from A2, times 0.08, the probability that it was broken, which gives me 0.032. So 3.2% chance that it's broken given that it came from the second machine. And then the probability that it came from A2 and it's not broken is the probability that it came from A2 times the probability that it's not broken given that it came from A2. So the probability it came from A2, 0.4. The probability that it's not broken given that it came from A2 is 0.92, which equals 0.368. So Cheryl asked John some questions to see if he understands what he drew out. So if a bottle is chosen at random, determine the probability that it is a broken bottle produced by machine A. So it's produced by machine A and it is a broken bottle. That's this probability. So that's the probability that it's from machine A and it's broken, which would be 0.03. Which of the following outcomes in the diagram relate to the event a bottle is not broken? Well, the events in which a bottle not broken is the probability that it came from the first machine and it's not broken, or the probability that it came from the second machine and it's not broken. So if a bottle is chosen at random, determine the probability that it is not broken. Well, the probability of this event occurring is right here, 0.57. The probability that it's this event, A2 and not broken, is 0.368. The OR means to add them together, which together gives me a 0.938 chance. So I have a 93.8% chance of the machines producing a non-broken bottle. I'm going to pause for a minute and then we'll go into the next part. Okay, this is the last question for this lesson. As part of an experiment into a learning process, a mouse is put into a maze and it is rewarded every time it makes a turn to the right. If the mouse turns to the right, the probability that it will turn to the right the next time is increased by 20%. If it turns to the left, the probability that it turns to the left next time is decreased by 20%. Assume that there's an equal probability that the first turn will be either to the left or to the right. So if we let R1 and L1 represents the events, R1 being the first turn is to the right, and L1 meaning the first turn is to the left, respectively. What would be meant by the event R2/R1? This would represent the probability that the mouse turns to the right a second turn given that the first turn was to the right. So R2, R1 means that the second turn is to the right given that the first turn was to the right. So determine as an exact decimal, what is the probability that the first turn is to the right? Well, if we read back, again it says assume there's an equal probability that the first turn will be to the left or to the right. So the probability that the first turn is to the right is 0.5, or a 50% chance. The probability that the first turn is to the left is also a 50% chance. So then the probability that the second turn is to the right, given that the first turn was to the right. I have to go back up to the top of the page and to the question. If the mouse turns to the right, the probability that it turns to the right the next time is increased by 20%. So if it's increased by 20%, that becomes 20% of the 0.5 that I had in the previous round. Because it was a 50% or 0.5% chance, and now I'm going to increase that by 20%. This becomes 0.2 times 0.5, which is 0.1. So I have 0.5 plus the 0.1, which gives me 0.6. I now have a 60% chance that the second turn will be to the right. The next one is, what is the probability that the second turn is to the left, given that the first turn is to the left? So this one was a decrease by 20%. So this becomes 0.2 times 0.5, which is the 0.1 again. So this would become 0.5 minus 0.1, or a 40% chance that the second turn will be to the left, given that the first turn was to the left. In part C, we're asked to put the probabilities onto a tree diagram and then complete the tree diagram. So we start off with the first outcome. Either the mouse is going to turn to the right or it's going to turn to the left. The probability of each is 0.5. Then I have the second turn. This is the probability that it turns to the right versus the probability that it would turn to the left. The probability that it turns to the right, we calculated above, is 0.6, which means the probability that it would turn to the left would be 0.4, because it has to add up to 100. If the mouse goes to the left, and then goes to the right the second time, and then goes to the left the second time. This one I have done. That's this right here. So that's 0.4, which means by default this has to be 0.6, because that's how I add it up together to get my 1.0. So now I can put my final outcomes. The probability that the mouse will go to the right and to the right becomes 0.5 times 0.6, which becomes 0.3. So 30% chance. The probability that the mouse turns to the right and then to the left becomes 0.5 times 0.4, which equals 0.2. Then we have the probability that the mouse goes to the left the first time and right the second time. That's 0.5 times 0.6, which is 0.3. And finally, the probability that the mouse goes to the left the first time and left the second time becomes 0.5 times 0.4, which is 0.2. So that's my tree diagram. Now I need to answer the questions. So the probability that the mouse goes both directions, or the first two turns are both to the right, is 0.3. The probability that it goes to the left both times is 0.2. The probability that they are different, meaning it goes to the left, or sorry, goes to the right, then to the left, is 0.2. And the probability that it goes to the left and then to the right is 0.3. Together gives me 0.5. And that's using tree diagrams to solve probability. So the questions that I want you to work on: 3, 5, 7, and 8, 10, and 11. We will go through these, or I will answer some questions on them a little bit on Friday. Between now and Friday, tomorrow is the Eli event, the post-secondary. Like I said before, there's like just about 21, 22 different post-secondary institutions from across Alberta that will be at it. And then you'll have a review assignment that I will have ready for you on Wednesday morning for you to work on when you're done the ELA event. Thursday you have a quiz, which is on lessons 1, 2, 3, and 4 from this chapter. So chapter 4, lessons 1, 2, 3, 4. It's written on the sideboard as well so that you don't forget. And then the remaining time in class on Thursday will be to work on the review assignment. And then I'll be back on Friday. So we will see you guys then. Take care.